All right, so now we get somewhat trickier. Limiting reactant. So this is stoichiometry on steroids, basically, okay? So you've got a chemical reaction, and most of the time, for reasons you'll probably learn in 1212, you don't have exact stoichiometric equivalents of both reactants. You typically have an overload of one or an excess of one and a deficit of the other. There's some good reasons for that, though. So again, as you'll learn next semester in 1212, if you add excess to one of the reactants, you can typically not only speed up the reaction, but obtain more product. So you want to, it turns out though that the reactant that's in deficit, or that is the limiting reactant, the one that's going to run out of first, is going to determine how much product you can make, right? Because as soon as you run out of the limiting reactant, the reaction stops, right? It can't keep on reacting and making product with only one reactant. So the limiting reactant is basically the weak link. It's going to determine everything. It's going to determine how much product you make. And so the amount of product that the limiting reactant is capable of making, if at all converted, is called theoretical yield. Okay. So those are two vocabulary words you need to be real comfortable with, okay? Here's using a chemical reaction instead of hot dogs, okay? So look at this balanced reaction, which represents the combustion of CH4. And when I say stoichiometric amounts, if I had exactly 1 molecule of methane and 2 molecules of oxygen, I could get, my theoretical yield would be exactly 1 molecule of carbon dioxide and 2 molecules of water, right? But what if I skew the amounts I start with so I'm not using stoichiometric amounts? In other words, I have an excess of one and the other is a limiting reactant. So you need to be able to determine which one is excess and which one is limiting, because it's the limiting one that's going to determine how much product you can make. So this is simple math. Hopefully you can do this with mental math. So if I have 5 methane, so if I put a 5 in front of that, how many oxygens do I need? Well, remember to look at the mole ratio, right? So if I start with 5 moles or 5 molecules of CH4, how many moles of oxygen do I need? The mole ratio will tell you that, right? So look at the balanced reaction. For every 1 mole of CH4 that I use, I need 2 moles of oxygen, right? So that means if I start with 5 moles of methane, I need 10 moles of oxygen, right? I don't have 10, I only have 8. So that tells you that oxygen is the limiting reactant. Now this one is pretty easy to just do using mole ratios. That won't be the case as we get to more complicated problems. So I'm going to give you a method that works 100% of the time. It's pretty tedious, but it's very, very reliable, okay? And what it is down at the bottom here. You are going to calculate the amount of product, doesn't matter which product as long as it's the same one for both of them, the amount of product that could be made for each of the given quantities of the reactant. And you will find that the excess reactant will be capable, clearly, of making more product than the limiting reactant. Look at that a little bit closer. All right, so for example, if I start with 5 moles or molecules of CH4, and I want to know how much product I can make, I'm just going to pick a product. Doesn't matter again, as long as it's the same one you use for the other reactant. And so I'm going to now use the mole ratio to figure out how many moles of product I can make from this 5CH4. And it turns out I can make 5. So remember that number. I can make 5 product molecules, 5 CO2, right? So now I'm going to go and see how much CO2 that 8 moles of oxygen can make. And I'm going to compare. Okay. So I'm going to do the same thing starting with oxygen. If I have 8 moles of oxygen, how much CO2 can I make? Well, mole ratio again between oxygen. Okay, 2 oxygen makes 1 CO2. And it turns out I can only make 4 moles of carbon dioxide from this amount of oxygen. Do you remember on the last slide, it said that I could make 5 moles of CO2 from the CH4 that I started with? Okay, the 5 moles of CH4. All right, so here's the important part. The reactant that makes the least amount of product is the limiting reactant, okay? The reactant that makes the least amount of product is the limiting reactant. And that's how you are going to identify limiting reactant 99% of the time. You've got to do a quick stoichiometry to product for each of the reactants, decide which one makes the least amount. Now, I want to point out something really, really, really important. So if you're kind of spacing out at me, pay attention. Okay, this is very important because it's a trick. It's a common trick on standardized exams for you. What if you weren't thinking or you had test anxiety, right? And you were just given these two and it said, which one's the limiting reactant? CH4, 2O, or oxygen? It has nothing to do with comparing the amounts of each you start with in grams, okay? Or moles, whatever. Notice that we have less of the CH4 than we do of the oxygen, but oxygen's a limiting reactant, right? So it has nothing to do with the overall quantity of the starting reactants, because you have mole ratios and molar masses and all sorts of stoichiometry there that's going to affect how much of each of them you need. So don't get fooled into this by just saying, well, this number's smaller, it's got to be limited. No, that's not the case. You have to go through the stoichiometry that I just described here. All right, here's one for you to try. This is a really important one, okay? Because it practices everything we've learned so far in moles and stoichiometry, okay? You're going to do all the calculations from grams to moles, mole ratios, and you're going to determine limiting reactant. You're going to determine theoretical yield, okay? So take your time, go back a couple slides if you need to, and that's going to be so important for your learning rather than just watching me do it. That's not going to teach you a whole lot. Just a couple other tips here. How do you know that you're dealing with a limiting reactant problem and not just a regular stoichiometry problem? Whenever you're given quantities of both reactants, so see, this tells me I have 100 grams of nitrogen and 50 grams of hydrogen. If you're given quantities of both, that's a limiting reactant. And before you do anything else, you need to determine what the limiting reactant is, right? So I've got to do stoichiometry with both of these reactants to figure out how much product they can each make. And remember, the one that makes the least amount of this NH3 is going to be your limiting reactant. And it's the quantity made by the limiting reactant that's the theoretical yield, which is what you're looking for. Anyway, give it a shot on your own, then come back. All right. I'm going to do nitrogen first. So, and remember that decimal is telling you that has 3 sig figs, right? So that'll be important eventually. So 100 grams of nitrogen. I know my first step is always to convert the material I'm starting with to moles. Since I have grams, I've got to use molar mass on the periodic table. Make sure you carry plenty of digits in your molar mass. The molar mass of N2, nitrogen's a diatomic, so it's 2 nitrogen atoms. All right, so now that would give me moles of nitrogen. Now I'm going to use mole ratio to get to the product. Remember, I'm trying to figure out which of these reactants makes the least amount of product. So I'm going to put moles of N2 in the denominator so it cancels. And I know from the balanced reaction there's a 1 in front of that. And I'm trying to get to the product, which is NH3, and there's a 2 in the balanced reaction with that. All right, so if I were to stop now, I can stop now. Yeah, I'll stop now. 2 moles of NH3. Now we got to figure out, and you could take it to grams if you want to, but it's a little bit less work to stop at moles. Now I'm going to do the same thing for hydrogen, and I'm going to figure out how much NH3 that 50 grams of hydrogen can make. So hydrogen's another diatomic, so be careful. Its molar mass, need 2 hydrogen atoms. And okay, so once I get it into moles of hydrogen, I'm going to use a mole ratio to convert that to moles of NH3. Now hydrogen has a coefficient of 3 in the balanced reaction. And of course NH3 has coefficient of 2. All right, so now I am going to calculate both of these and determine what my limiting reactant is. So 100 divided by 28.02 times 2. So that tells me 100 grams of nitrogen can potentially make 7 point. I'm going to carry extra digits for now because I can't remember, but I think I have to go to grams. All right, so that can make that around 7 moles of ammonia. Let's see how much the 50 grams of hydrogen can make. Ooh, that can make 16. And again, I'm just putting extra digits for now, okay? All right, so what is my limiting reactant? It's the one that makes the least amount of product. All right. So that's not my limiting reactant. That's my theoretical yield. My limiting reactant, you have to go all the way back to where you started. This is my limiting reactant. And so that means from here on in, don't use anything to do with the excess reactant, okay? Don't do anything with it. So now if the problem had asked for how many moles of NH3 can be made, that would be your answer, but typically it'll ask for grams. And so once you have the limiting reactant, you would go ahead and do one more calculation to get grams. And so the molar mass of ammonia is 17.04 grams per mole. And so now, if we multiply those out, they will give us the grams, the theoretical mass that can be made. So 7.1378 times 17.04. Right, so the theoretical yield, and now I'm going to round it to 3 sig figs because that's what I started with. Theoretical yield is 122 grams of NH3 can be made. That's the theoretical yield. Remember, the theoretical yield is the amount that can be made by the limiting reactant. All right. We've talked about theoretical yield quite a bit, but it turns out there are 3 different types of yield. There is theoretical yield, which is the calculated amount that the limiting reactant can make. There is actual yield, which is what the chemist actually makes in the lab. Okay, so the actual yield, theoretical yield, is that if everything was perfect and 100% of the reactant converted. That never happens, okay? You're usually lucky as a chemist when you get at least 70% yield. So the actual yield is going to depend on the conditions of the reaction, equilibrium, all sorts of things. And then, of course, there's percent yield. So you need to know the difference between all of them. actual yield must be given to you, okay? Because it's going to depend on the equipment you have, the chemist, how long you let it go, all sorts of things. So that has to be given to you in a problem. Now, of course, chemists always want to know what the actual yield is compared to the theoretical yield, right? What ratio of the product did they get from what they could have gotten? And that's percent yield. So this is a formula you need to know, okay? Percent yield is simply the ratio that the chemist gets, the actual yield over the theoretical yield, the calculated amount that could have been made, times 100. And so that's a real common thing to have to calculate. So here's another example for you to try. Let's see, 14.4 grams. I like to write the given information under the chemical reaction. It just kind of helps me visualize what I'm trying to do. 14.4 grams of aluminum. When a reaction says excess, that means it's not a limiting reactant. They're telling you what the limiting reactant is. They're telling you that aluminum is the one that counts. It's a limiting reactant. It's all you need to do a calculation with. So you can just kind of ignore the other one. All right, so the first thing you need to do is to calculate the theoretical yield. Now you have two products, so which product are you going to go to? The one they ask you about, okay? They're asking you about hydrogen. So again, you're going to ignore the other one. So you're trying to find out how much hydrogen you can get. So what is the theoretical yield of the hydrogen? Once you calculate that, theoretical yield is always what you get from stoichiometry. You want to calculate percent yield. So what is this they gave you here? That's the actual yield, right? Anytime they give you an amount of a product that's collected, that is the actual yield. And then remember your percent yield formula, right? It's going to be the actual yield, which is 1.05 grams, divided by the theoretical yield that you calculate, right, times 100. So go ahead and give that a shot, and then come back here and I'll work it out for you. Start with a given, of course, always. 14.4 grams of aluminum. Now remember, the process that we're almost always going to go through, right, is grams of whatever the given information is. First thing you have to do is go to moles of that substance. Once you're in moles of that substance, you can use mole ratio to go to moles of any other substance in the chemical reaction. And then finally grams of that. So almost always, it's going to be a three-step calculation. So we need the molar mass of aluminum to convert to moles of aluminum. Okay, now that I'm in moles of aluminum, I can use mole ratio to get to the substance the problem is asking about, and the problem is asking about hydrogen. I'm going to go to the balanced reaction to get the coefficients for the mole ratio. So there's a 2 in front of the aluminum and a 3 in front of the hydrogen. If I were to stop here, my units would be moles of hydrogen. The problem is asking for grams. Well, I need to find grams, theoretical yield. And so I need the molar mass of hydrogen, which is diatomic. So it's 2 hydrogen atoms. All right, so all of that's going to give me the theoretical yield for hydrogen. That is, how much hydrogen can be made if all of the given aluminum is reacted. So I'm going to go ahead and plug that into my calculator real quick. And I get that I can make 1.62 grams of hydrogen. That is my theoretical yield. Okay, now I'm going to calculate percent yield. So the percent yield is the actual, which was given, 1.05 grams divided by theoretical, 1.62 grams, times 100. And let me punch that in real quick. And I get that the yield is 64.8%. That's it. Now we're going to finish. The last topic in this lecture is how to calculate how much excess reactant is left over. That happens to be a type of problem that I typically give as a bonus question on my exam. It's a little bit higher level, which is why I count it as bonus. But here are the basic steps involved. You always have to find limiting reactant. That's the first thing you do to find quantities of anything, theoretical yield, but also how much excess reactant. Once you know what the limiting reactant is, you will use that and stoichiometry to figure out how much excess reactant actually reacted or how much was used up, right? So you're just going to use the mole ratio between the limiting reactant and the excess reactant to calculate how much of this excess reactant did I actually use in the reaction. Once you have that, how much was actually used, you can subtract how much was used from the initial amount of excess reactant. So let's say the problem told you that you had started with 25 grams of some excess reactant A, and then you did a calculation with your limiting reactant and you found out that you only used 20 grams or only needed 20 grams of A. That would mean that your excess reactant that was left over would be the difference between those. All right, so here's a sample problem for you, kind of walks you through it. And so if you're in my class and you want to get a bonus on the next exam, you can become an expert at this, okay? So here's a typical limiting reactant problem. You know it's a limiting reactant problem because it gives you quantities of both reactants. So I'm going to figure out how much each of the given amounts of reactants, how much product they could theoretically make. The one that makes the least, okay, so this is the theoretical yield, right? The one that makes the least is the limiting reactant. So iron 3 chloride was the limiting reactant, which means hydrogen sulfide was the excess reactant. All right, so now how much of this excess reactant actually got reacted? To figure that out, everything depends on the limiting reactant, right? So again, you're going to start with the limiting reactant now that you know which one it is, and you are going to use the mole ratio now between the limiting reactant and the excess reactant because you're trying to figure out how much excess reactant actually reacted. So that will give you how much of the excess reactant reacted. You know how much you started with, right? You started with 52 grams of that excess reactant. So you subtract what you just calculated here. Ooh, where did I get 27.4? I changed it. That should be 28.4. But anyway, so you subtract the amount that actually reacted from the amount you started with, and that gives you the excess reactant that's left over or unreacted. That is it for this PowerPoint.